This video is for Section 6.1, Discrete and Continuous Random Variables. So a definition for a random variable, it takes a numerical value that describes the outcomes of some chance process. Another very important definition for this section is probability distribution, and that's the possible values and probabilities for a random variable. A discrete random variable, x, takes a fixed set of possible values with gaps between. The probability distribution of a discrete random variable lists the values x sub I and their probabilities p sub I. And like the 1, the 2, the 3, those would all be like separate discrete random variables. The probabilities p sub I must satisfy two requirements. Every probability p sub I is a number between 0 and 1. The sum of the probabilities is 1. So p sub 1 plus p sub 2 plus p sub 3 plus, and then it kind of continues on as however long it needs to go until it reaches 1. And to find the probability of an event, add the probabilities p sub I of the particular values x sub I that make up the event. So an example of that is the following problem. So in 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of newborns. What Apgar scores are typical? To find out, researchers recorded the Apgar scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. That's our chance process. Define the random variable x equals Apgar score of a randomly selected baby 1 minute after birth. The table below gives the probability distribution for x. So we see in our table that we have our values, and they go from 0 to 10, just like it said up here. And then we see the probabilities that are associated with each of those values. So A says, show that the probability distribution for x is legitimate. So in order for us to show that the probability distribution for x is legitimate, there are a couple of criteria that it has to meet. The first one is that every single one of the probabilities is between 0 and 1, and that's true. And the other is that they have to all add up to 1. So if I went to add them all up, that should be, there we go. All right, so when we add them all up, they all add up to give us 1. B says make a histogram of the probability distribution and describe what you see. So remember that whenever we make a histogram, that it kind of looks like a bar chart. And so for B, nope. On the y-axis, we would have the probabilities. So none of our probabilities are bigger than 0.5, so we'll make the top 0.5. Mine's off a little bit, so I'm going to change this one. And then my x values would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. For 0, the probability is 0.001, so it's just like barely even there. For 1, it's 0.006, so we can kind of sort of see it a little bit. For 2, it's a little bit bigger than that. And for 3, it's a little bit bigger than that. So it was 4. And 5. 6. 7 shoots way up, so it's almost 1. 8 shoots way up, so it's above 3. That one's a little different. 9 is almost 5, or 0.5. And 10 is small again. So if we have to describe what we see that this data is heavily skewed to the left. And that tells us that a randomly selected newborn will most likely have an APGAR score at the high end of the scale, which means that the baby was pretty healthy at birth. There's a smaller chance of getting a baby whose APGAR score was 5 or below. And so we can tell that just by looking at the data that we have on our histogram. C says doctors decided that APGAR scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected baby is healthy? Alright, so if we are finding the probability that a baby has an APGAR score of 7 or higher, then that means that we're going to let X, which is going to represent our APGAR score, that it's going to be greater than or equal to 7. So if it's greater than or equal to 7, we're going to 10. So that means that we would say the probability X equals 7. We would add to it the probability that X equals 8, plus the probability X equals 9, plus the probability that X equals 10. So the probability that X equals 7 is 0.099. Probability that X equals 8 is 0.319. 9 is 0.437. And 10 is 0.053. And so we would add all of those up together, and it would give us 0.980. And so that is approximately 91%. And so that would mean that you had about a 91% chance of randomly choosing a healthy baby. So check your understanding. North Carolina State University posts the grade distributions for its courses online. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Statistics 101 student at random. The student's grade on a 4-point scale with A equal to 4 is a discrete random variable X with this probability distribution. So on number 1 it says, say in words what the meaning of the probability X is greater than or equal to 3 is, and then what is that probability? Alright, so if we are saying that the probability of X is greater than or equal to 3, then that means that we are saying, because we know that 0 is our F's, 1 is our D's, C is 2, and 3 is B, and 4 is A, based on this information here, then that means if the probability of X is greater than or equal to 3, that we're talking about a student or students getting A's or B's. It then asks us to calculate that probability. So the probability that X is greater than or equal to 3 would be the probability that X was equal to 3 plus the probability that X was equal to 4. So we can see in our table that the probability X is equal to 3 is 0.42. And the probability X is equal to 4 is 0.26. If we add those together, we get 0.68. Or about 68%. Two says, write the event the student got a grade worse than C in terms of values of the random variable X, and what's the probability of this distribution? If we talk about a student got a grade worse than a C, then that would mean that they either got a D or an F. And so if we were finding the probability of that, we would say probability X is less than 2. The reason I chose 2 is because 2 represents C. It doesn't say that a student got a grade of C or worse. It says a grade worse than C. So that means either a D or an F. It also asks you to calculate the probability for that. So the probability that X is less than or equal to 2 would be the probability that X was equal to 0 plus the probability X was equal to 1. Probability that X is equal to 0 is 0.02 because that is the number that is associated with F's. And the probability that X is equal to 1 is 0.110 or 0 because 0.10 is the probability that is associated with getting a D. So if you add those together, you would get 0.12. And so you would have about a 12% chance that a student got worse than a C. Three asks you to sketch a graph of the probability distribution and describe what you see. So when you have to sketch a graph of a probability distribution, your best bet is to do a histogram. So if I look back at my table, I see that my y-axis should be no more than about 0.5 because my highest one is 0.42. And then across the bottom, I would have 0, 1, 2, 3, and 4. Zero represents my F's, and so the probability of that is 0.02, which would be down here very, very close to the bottom. Probability that X was equal to 1 is 0.10. Probability X was equal to 2 is 0.20. Oh, this one is super, super off, but you get the idea. Actually, let me back up a second. This one is really here. This one is really here. Probability of 3 is 0.42, so this one goes way up here. And probability of 4, or X equals 4, is 0.26, so it's somewhere here. So if we look at this one, it looks like our graph is kind of left skewed. And so what that would mean is the higher grades are more likely, but there are a few lower grades. All right, next we're going to talk about the mean or expected value of a discrete random variable. So suppose that X is a discrete random variable whose probability distribution is shown in the table. To find the mean or the expected value of X, multiply each possible value by its probability and then add the products. So you would use this very confusing looking formula. Remember that this capital sigma just means the summation, and so we would sum up all of the values and multiply them each by their probability. So again, we're looking at the APGAR scores that we talked about earlier. So we define the random variable X to be the APGAR score of a randomly selected baby. The table below gives a probability distribution for X once again. And so it asks us to calculate the mean of the random variable X and interpret this value in the context. Alright, so what we would need to do, we would be finding the mu, or the mean, of X. And so the way that we would do that is we would say, okay, we're going to take each of the values and multiply it by its probability. So 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007 plus 3 times 0.008 plus 4 times 0.012 plus 5 times 0.020 plus 6 times 0.038 plus 7 times 0.099 plus 8 times 0.319 plus 9 times 0.437 plus 10 times 0.053. Whenever you add all of those up, you would get 8.2 or 0.128, which is going to mean that the mean APGAR score for a randomly selected baby is 8.128. This is the long-run average APGAR scores of many, many randomly chosen babies. Next, we're going to talk about variance and standard deviation of a discrete random variable. So suppose that x is a discrete random variable whose probability distribution is shown in the table, and the mean of, and that is the mean sub x is the mean of x. The variance is this formula, which is just the way that you calculated variance before. So you would take the standard deviation and square it, and that would give you your variance. To kind of go backwards from that, the standard deviation is the square root of the variance. So again, looking at APGAR scores, this time we want to calculate measures of the spread, so that would be the standard deviation and the variance. And so in the last example, we calculated the mean APGAR score of a randomly chosen newborn to be 8.128. The table below gives the probability distribution for x one more time, and we want to calculate the standard deviation of the random variable x. So what we are going to do to find the standard deviation, this is going to look like this. And so remember that in order to find standard deviation, you are going to take the value and subtract out the mean. You're going to square that, and you're going to multiply it by the probability. So you would do that for each of these. So you'd say 1 minus 8.128 squared times 0.006 plus 2 times, 2 minus 8.128 squared times 0.007. And you would continue with this same pattern until you got to 10 minus 8.128 squared times 0.053. Whenever you work that out, you would get 2.066. This would represent the variance. And so then in order to get the standard deviation, you would take the square root of 2.066, and that would give you 1.437. On average, a randomly selected baby's APGAR score will differ from the mean, which is 8.128, by about 1.4 units. Check your understanding. A large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is follows. So for number 1, we need to calculate and interpret the mean of X. So to calculate the mean for X, you would say each of the values, which would be the cars sold, times their probability. And eventually, when my pen starts working again, I can do that for you. There we go. All right, so the mean would look like 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1. So obviously the first one would be 0. The second one would be 0.4. The third one would be 0.4. And the fourth one would be 0.3. So whenever you add all of those up, it would give you 1.1. Next, we need to calculate and interpret the standard deviation of x. So we first have to start by finding the variance of x. And so to do that, you would have to do your value minus your mean times your probability. And you would add all of those up. So if you do that, it would look like 0 minus 1.1 times 0.3 plus 1 minus 1.1 times 0.4 plus 2 minus 1.1 times 0.2 plus 3 minus 1.1 times 0.1. Whenever you do that, you would get 0.889249. And then to find the standard deviation of that, you would take the square root of that. And so when you take the square root of that, you would get 0.943. Let me write out the steps for that. So you would take the square root of 0.889249. And whenever you did that, you would get 0.943. A continuous random variable x takes all values in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area underneath the density curve and above the values of x that make up the event. So this example is about young women's height. So normal probability distributions is basically what we'll be looking at. So the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. This is a distribution for a large set of data. Now choose one young woman at random. Call her height y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. Find the probability that the chosen woman is between 68 and 70. Alright, so for this one we're going to state what our plan is, or what our question is. And so our question is, what's the probability that a randomly chosen young woman has a height between 68 and 70. The plan is we're going to say the height y of the woman we chose has a normal distribution 64 2.7. So remember, the first one represents the mean, second one represents standard deviation. So we want to find the probability that our y is between 68 and 70. So we have to find the area underneath that curve. So to do that, you have to find the standardized scores. So remember, that's the z-score. So the z-score would be equal to 68 minus 64. So our observed minus our mean divided by our standard deviation. So our first first z-score would be 1.48. The second one, we would do 70 minus 64 over 2.7. And when we got that, we would have 2.22. And so basically, we would have our distribution, and we would be looking from 68 to 70. And so because we're looking for the area in here, we would use normal CDF. So our lower bound would be 68. Our upper bound would be 70. Our mean is 64, and our standard deviation is 2.7. Whenever you work all of that out, you would get 0.0562. And you can work this out on your calculator, but your class starts in 9 minutes, and I'm trying to get through this video. And hey, I might be able to do that for you. All right, so let me do that real fast. All right, so you would go to second bars. You would do 2. Your lower bound is 68. Your upper bound is 70. Your mean is 64. And your standard deviation is 2.7. And so, just like I said, it would be 0.062. Actually, your book gives you a wrong answer, because that would really just be 1. And look, your class is starting. Bye.